This is for Kurt and Elon to explain our technology. We want to use this in the Tesla. We want Elon to bring this to market. We know that the educational system, the military, and I'm not too excited about bringing this to Toyota, which Jonathan has relationships with the folks in Toyota. He has a number of patents with them, but let's discuss the energy density. Liquid fuels have 10 times the energy density of batteries. Batteries have 10 times the energy density of supercaps. Supercaps have 10 times the energy density of electrostatic ceramic capacitors. We have created a new generation of ceramic capacitors that rival supercapacitors. We can create a new generation of ceramic capacitors that are more dense than batteries. Here's where the technology was. Back in 1995, they were using 4 micron technology. They could get 4.7 microfarads. Then in 2005, they're 100 microfarads. Now we've extrapolated where we are at 2,500 here compared to the lithium ion. Here's where lithium ion, this is what's in the Tesla right now. We're up here. How are we up here? We're going to show you how we're up here. Look at the dielectric constants. Supercapacitors 10 to the 5. Our capacitor 10 to the 10th. Why? It's because we have a high permittivity and polarized drop model. We have a simple extrapolation that suggests the energy density higher than lithium ion carbon batteries, lithium tin, or even lithium silicon, which are very expensive to make and require costly materials. Where does this come from? Here's the fundamental equation. We all know this. With a thickness of 2.5 microns, 10-year-old technology, easy to do. V equals 1 volt because we're using water. We're breaking down at 1 volt. And only 50% of the volume is dielectric. It's very easy to do. Yields an astounding 9,000 joules per cubic centimeter. What happens when we do this? We changed the thickness to 0.5 microns, regularly attained with standard ceramic capacitors, 2.5 volts using a novel electrolyte with high dipole moments, and 75% volumetric of the volume of the dielectric. We've got 2 million joules per cubic centimeter. Using 0.5 microns, 75% dielectric, and 2.5 volts, 2 million joules per cubic centimeter. In other words, we could run a D-cell size 100-watt light bulb for 300 hours. Hello? Capacitors, being capacitors, decrease their voltage in time. Put a capacitor to charge a small battery, and you have an endless supply of energy to give to the battery that holds the constant voltage. The equation is C equals K epsilon A over T. The dielectric constant is stuck at 10,000 for barium titanate. Our dielectric constant is 25 billion. How do we get 25 billion dielectric constant? We take advantage of the dipole moments of the electrolyte. More on that in a second. Here's a test circuit we used, and here's the actual capacitor. Insulating material, front and back part, and the dielectric. These two plates are equivalent. We put forth the pressure between the two plates using a novel method that created the 2.5 microns we speak of. And charging and discharging in time. This is the response we see with this rather caveman capacitor. When we vary the thickness, 1.47, 2.46, 2.8, 4.3, the thickness, we see the function of thickness in time. The thinner the material is, the longer the time is. Now, this is 1.47 millimeters. It's insanely fat. Remember, existing technology does 0.5 microns. We show also some data with 2.5 microns. We're at 1.47 millimeters. This graph you might want to pause, but remember, a perfect barium titanate, the K is 10,000. We're 500 million. That when we go, this is at 2.5 microns, when we go to 0.5, we square the thickness, that goes to 25 billion. So this is 2.5 microns. Pause this and look at some of these numbers. Here's a graph just to gain an insight between the inverse thickness and capacitance. You can get a sense of that. To put it in perspective, remember we always refer to a D-sized battery with a volume of 53 cubic centimeters. Half of that volume is taken up by the super dielectric material of 5 micron thickness. The rest of the volume is divided between the electrode and insulating values, which means our NPS capacitor called 25,000 joules. The best D-cell supercapacitors advertise a capacitance of actually 11,000 joules versus 25,000. A typical D-cells battery can deliver just over 80,000 joules. So with a very little optimization on the super dielectric materials of remarkably inexpensive materials, can rival batteries in terms of volumetric energy density. What will that look like? It looks like this. Remember, supercapacitors 11,000, the NPS 25,000, generation 1 without extrapolation 100,000 joules per D cell, and a battery is 80,000. So we have surpassed a standard battery. This includes lithium-ion batteries. What's the mechanism of action? The mechanism of action is taking advantage of the dipole moments as the ions move from the plus side to the minus side. This Jonathan can explain more in detail, and you'll probably get that better than I can possibly explain. Here's a discharge time for a 0.2 millimeter, 2.5 centimeter with 10K. Takes 40,000 seconds to go down. Another graph showing multiple discharges, 3 full cycles. Another graph showing 3 discharges on a certain date. Yet another graph. Prove no materials were consumed. We let the dielectric dry, cracked and flaky with no measurable capacitance. All we had to do was add water back, and we got our original super dielectric behavior. Asking of you to do, Kurt, you said you were familiar with supercaps, and the challenge is the energy density is too low. I hope that the presentation I've given you has demonstrated that the energy density is much higher than supercaps, and we can make a supercap that will compete with lithium-ion carbon batteries, even lithium-ion tin, or even lithium-ion silicon batteries in the energy density. So we definitely would like to speak with you. We would like to speak with Mr. Elon Musk as well and introduce you to Jonathan. I'm going to give you the CV of Jonathan to read over, and I ask that you give me a call and we will set up a meeting, and I can show you that we have the necessary technology to bring what Elon was searching for, is the ultimate energy system for electric vehicles. As I said in the web, I do believe that Mr. Musk has the vision to bring this device to market. And Mr. Musk and Mr. Kelty may call me anytime. Here's my full contact info. And we want to meet with you guys and bring this thing to market. Where we are right now, there are potential negotiations with Toyota Company in Japan. And Jonathan knows the directors in the TEMA, which is in the battery division, the catalysis division. And Jonathan's, another one of his skills is optimized catalytic conversion systems, as well as fuel cells. We want to work with Tesla to bring this to market, create a laboratory where we can do this and demonstrate and bring this to market. I don't want to bring it out of the United States. My concern is having it go to the government or go to some private industry. or the educational field that doesn't really do much with anything. This is a very common problem in bringing things to market. I don't want to experience some regrets, like imagine being Southern Pacific and us not driving Southern Pacific electric cars, trains, and airplanes when they owned most of the real estate. Same thing with Kodak Camera Company. How come we don't have Kodak digital cameras? And think of the Wright brothers, the two bicycle mechanics who didn't get funding on their airplane until they flew it around Paris a number of times, doing loops and circles, until they had the complete flight systems designed. We have something that's ready to go that will use a hybrid system that will use this new technology to deal with the 500 kilogram battery that's presently used in the Tesla, and we could reduce that to 125 kilograms with a hybrid system using this new paradigm technology and with standard batteries. So we're ready to go. My number again is here, 831-455-0418, and I'm going to give you a link to the CV of Jonathan. Thank you very much.